All right, so we're going to start talking about a little bit more concepts of statistics and hypothesis testing. Stuff's going to get a little bit more conceptual than it is going to be computational. We've done a computational now for the last couple of chapters with conducting hypothesis tests in particular. But this is going to get more about behind the scenes, some of the nuts and bolts, if you will, for why things work the way they work. So to start this off, we're going to talk about the concept of sufficient statistics. Now, certainly, we've already used statistics to help us estimate population parameters. Usually when we calculate a statistic, we call that a point estimate for a parameter. So we've certainly done that with some random samples and those kinds of things to estimate them. However, a natural question, hopefully it's a natural question, is how do you know that you've squeezed out every single bit of information about that parameter that you can from that one sample that you have? Okay, so that's what we're interested in when we talk about sufficient statistics, is how do we know that we've actually gotten every single bit of information about the parameter that we possibly could get? All right, so I'm going to try to do this with a couple of different examples and then go through the definition of what we mean by sufficient statistic. So let's say we have a random sample from a Bernoulli distribution. Remember, a Bernoulli distribution is just a single Bernoulli trial. So each xi here can be either 0 or 1. And the probability that you actually see 1 is p. That's the parameter we're talking about. So p, again, is representing that probability of success, if you will. But it's a single trial. It's not like the binomial distribution where we've done trials over and over and over again. All right. Well, since we have a random sample, each of the x's are independent. So the probability that capital X1 equals little x1, capital X2 equals little x2, and so on is just the product of the individual probabilities for each of those x sub i's. And remember, for Bernoulli, it's just p to the x, 1 minus p to the 1 minus x for the PMF in this case. So when we do the product of all of these, this is what we get. Now, using our law of exponents, of course, when I multiply these p to the xi's together, I'm going to add the x sub i's together. When I multiply the 1 minus p's all together, I get n here, and then minus the sum of the x sub i's. Whoops, sorry. So notice that in the exponents here, I see the sum of the individual x sub i's. Now let's think about how we actually get an estimate for p, just in general. We would add up the x sub i's. Basically, that counts up the number of ones that we get, and we would divide by n. That gives us the percentage of ones that we would get, and that gives us our point estimate for what the population parameter p should be in this case. It's important to notice that I actually see that particular idea in this expression. We're going to come back to that. All right. So let's take y to be those sum of the x sub i's, adding up all those x's. Well, we know when we add up individual independent and identical Bernoulli random variables, we get a binomial random variable. So y is binomial in trials, and probability of success is p. So the PDF, or PMF I should say, for y is this expression. This is not unknown to us. All right, so let's consider the conditional probability. So knowing that you're given a specific y value, what's the probability that each of the x values were the x1 out to xn? All right, well, certainly if we're given y and the sum of the x's, by the way the y is defined, if the sum of these x's isn't equal to y, that probability is 0, without a doubt. Otherwise, if y is the sum of the x sub i's, then this probability is just, here's our conditional probability formula, right? It's the probability of the intersection over the probability of the given. Well, we just said that if y is equal to the sum of the x sub i's, well, in order for both of these things to happen, we have to have the first thing happen. So I can replace the top with just the probability of each individual xi equaling the little x sub I. We've already got formulas for both of these things. So I just plug those in, and this is just simplifying the top again. All right, But now remember, we're assuming in this case that the little y is equal to the sum of the x of i's. Well, if little y is equal to the sum of the x of i's, these pieces go away, or these pieces, I should say, are the same on top, right? The p to the y and the 1 minus p to the n minus y. Those are the same. They cancel, and we're left with this expression. Now, what's important about that expression? Well, notice that the conditional probability, if we're given the sum of the x's, then this probability of each individual x equaling is not independent of what p is. Okay? Depends on y, depends on n, but does not depend on the p. So then this means is that if given that we're given this particular summation, given the fact that we're given the capital Y equals little y, the individual values of the x of I don't provide any more information at all about the parameter p. We have exhausted the information from the sample using this statistic that we could possibly ever use to get an estimate for p. We don't have anything else that we can get from the sample. And again, that's all because if we're given y, this p goes away in the probability. So the probability that I had these individual x's is only dependent on the y, not the p. That's the idea. All right. So let's go to another example. So let's do a random sample from a Poisson distribution. We know that we typically use the lambda parameter to denote the Poisson mean, if you will. And let's let y be the sum of the x of i's again. Well, then we have another Poisson distribution. Y is definitely a Poisson distribution with the parameter n times lambda. All right, so like before, let's consider the same conditional probability statement. If the y's, again, remember we're given a value for y. Now I know y is equal to the summation of these x of i's, but we're given a particular value of what y could be. Right? This is just a value for what y could be. If it's not equal to the sum of these x's that we know, then I know the probability is 0 because I can't get these x's if it's not equal to the sum of the x of i's. Okay? So if we do have y equals the sum of the x of i's, go through the conditional probability again. Remember that this is your expression for your PMF for the Poisson distribution. This is the individual ones multiplied together. This is the combined one, right, where we said the new parameter was n lambda. Notice on top, then when I multiply these together, you'll add up the exponents. So that's why I have sum of x of i's here. This is a constant exponent, so I just have minus n times lambda there. And the best I can do is basically write out a product of those things in the denominator. All right, now again, remember that the summation of the x of I is equal to the y. So I get lambda to the y on top. And then I have a lambda to the y on bottom when I distribute that exponent to each individual factor. And now again, notice that the e to the n minus n lambdas cancel and the lambda to the y's cancel. And if we simplify, we just get y factorial over n to the y times the product of those factorials. This is not necessarily a nice formula to look at, but notice there's no lambda, right? The only thing that this conditional probability depends on, the probability that you got these actual individual x's given a particular statistic. Remember, we're thinking of this as a statistic. The probability that you got these individual x's given the statistic that you're using is this. There's no more information that these x's can tell you about the lambda. There's no lambda involved in the probability. So there's absolutely nothing else that those x's can tell you about lambda. The best you can do is use this statistic or a function of this statistic. What do I mean by a function of the statistic? Well, what do we typically estimate lambda with? Well, lambda is the mean of the Poisson distribution, right? So we typically use the summation of the x of i's over n as our estimate for lambda. That's a function of this statistic, right? It's a constant multiple of the statistic. It's a function of the statistic. All right, so sufficient statistics. Let's give a definition here. So let's let the x1 out to xn be a random sample. from some probability distribution with a parameter theta that we're trying to estimate. And let's let y be a function of the x1 out to xn, no theta involved here. And then we say y is sufficient for theta if the conditional probability doesn't depend on theta. Okay? So ordinarily we use what's referred to as, we did a lot of computations with the conditional probability, but ordinarily we use what's referred to as the factorization theorem to show that a statistic is going to be sufficient. So let's talk about the factorization theorem. We talk about having a random sample from that same probability distribution that was up in the previous definition. Let's actually specify what the PMF or PDF of the x's are. It's just going to write f of x theta. These are for each, remember these are identically distributed, right? Independent and identically distributed. So this is just a common PDF they're going to have. And let y be some function then of the x of i's. Then y is sufficient if and only if when I take the joint PDF or joint PMF, which in this case, since they're independent and identically distributed, that's just a matter of multiplying these things all together with the individual x of i's plugged in. We can write that as a product of two things. This is why it's called the factorization theorem. I've factored it into two pieces. The first piece is a function that they refer to as phi. It depends only on the x's through g. What I mean by that is the phi is basically a function of y with theta in it. Okay? Not x's individually that are needed, because think about it again, if y is supposed to be sufficient, when we do the conditional probability, that part's supposed to go away, that part that involves any of the parameter. So this parameter better not be involving with any x's individually. It better only be involved with y, because we're going to divide out when we do that conditional probability. And then x over here, what's left over, when we divide out by that conditional probability, if you will, what's left over only has x's in it. Okay? Doesn't have thetas in it. All right. Let's look at our Bernoulli example. Our joint PMF is this. When we factored out like this, we said that y was the sum of the x's. So I have p to the y, 1 minus p to the n minus y. So this part here is your phi, because it's phi involves the parameter p, but notice there's not individual x's here, it's just the y. Okay? And then, of course, our h function here is just a 1, because that certainly does not depend on theta. Okay, so anyway, that's what I just said without clicking. So let's look at the Poisson example. PMF, joint PMF, is the product. Here's the simplified version, like we talked about a couple of slides ago. Remember, our y was the sum of the x's. That was the sufficient statistic we were talking about. So I've popped this piece out with the lambda and this piece over here by itself. So notice that your phi here, if I let my phi be lambda to the y, e to the minus n lambda, this is a function of y alone involving the parameter, right? There's no individual x sub i's stuck in here. This is y by itself. And this over here is 1 over the product of those factorials and no thetas there. So we're breaking it into a theta piece, no x's, and an x piece, no thetas. That's what the factorization theorem says. So that tells us again that the sum of the x sub i's is sufficient for lambda in this case. All right. We're going to do lots more examples of this, talking through it in lecture. We're going to do a lot more other things with doing examples of these things, talk a lot more about the concepts. We're going to spend a lot of time on this. Like I said, this is not straightforward material at all. It's very, very conceptual. But again, the whole point here I want to emphasize is the reason we care about sufficient statistics is if you know your statistic is sufficient, then you know you've gotten everything possible out of a random sample that sample could ever possibly tell you about a parameter value. Okay? All right, so we'll talk a little bit about more of this in class.